M is the midpoint of BC. Then we draw the circumcircle of ABM, and it intersects AC at P. And we draw the circumcircle of ACM, and it intersects AB at Q. So let's see. So I wonder if I could make them, I want to make them both intersect the segments. Yeah, maybe something like that. Okay. So this is P, and this is Q. So then we draw the circumcircle of MPQ, and we want MP to be parallel to PQ. Interesting. I don't think I've seen a configuration like this before. So MT is parallel to PQ. So that would be point T. And then we draw the circle through T tangent to BC. Tangent to BC at point M. Okay, so we kind of want to draw the perpendicular bisector of TM. And okay, yeah, so and then we could draw the perpendicular at M, and that would be the center of the circle. So this point right here, and so D is the center of that circle. Let me hide a few things. There we go. It looks like D lies on AC, but yeah, we could do it like that. Oh, it still looks like D lies on AC. Oh, does D lie on A? I guess D does lie on AC. We'll have to prove that. That's interesting though. So GeoGebra kind of helped us there. The circumcircles of ABM and ACM intersect again. Oh, intersect the circle at X and Y. And we want to show XY is tangent to the circumcircle of ABC. That doesn't look right. Let's see. Is this problem correct? Or maybe it is. Let's see. It looks like EF intersects the circle twice, though. That's the thing. Maybe not.
A is on EF.
A is on EF. No, I did something wrong, I think. Or the problem's wrong.
I think you draw the circle wrong.
The circle omega?
Yeah.
Okay, so it's the circle, it's supposed to be through T and tangent to BC at M.
You draw the perpendicular bisector of TM in the perpendicular from M to BC.
Yeah, so these two, oh, you're right. D should not be the center. It looks almost like the center is is on the circle itself. So I guess we could prove that. Yeah, it looks like the center is here. And this is the circle. Okay, and then this is X and that's Y. So this would be, so X is where ABM meets it, and Y is this other point. And maybe X, A, and Y are collinear. So we'll see. That seems very likely, yes. Okay. So first, can we show that D lies on this circle? So yeah, how do we want to define this point D? Do we want to take the perpendicular at M and let it intersect this circle at D? I think that kind of would make the most sense, right? And then we would try to show that DT is equal to DM. Or we could draw these two circles and then we want to show that MT is parallel. Wait a sec.
We can define D as perpendicular from M to BC, and the circle PQM intersect at D, and we want to prove that DM is angle bisector.
We want to show that DM is an angle bisector.
Yeah. Can you let PQ and BC cut intersect?
Yeah. There we go. Yeah, so we want to show, MD bisects angle PMQ. Well, yeah, that's really the same as saying angle PMC is QMB, and that seems like it's probably an angle chase, right? Because angle PMC is PAB. Yeah, so I can prove that D is, I can prove that D is the center of omega. Because basically angle PMC is angle A, and angle QMB is also angle A. And so therefore MD bisects angle QMP. And once we know that, then DT equals DM, and yeah, everything else kind of follows from there. Okay, so we know D is the center of omega. Now we just have to show that XY passes through A and is tangent.
Can you delete E?
So we could show these angles out to 180.
Intersect XY with BC.
Right. I want this thing to go, there we go. I wonder if ET and P are collinear. No, that wouldn't make sense really. So it almost looks like P lies on AB. So I'm just going to move things around a little bit so it doesn't look like that. Okay, so maybe first we could show XA and Y are collinear, and then we could show their tangent. Well, I guess really we just can show that XA is tangent, and then by symmetry, YA would also be tangent, right? And the claim would follow. So we want to calculate angle XAB, and we want to show it's equal to angle ACB. Or I guess we could try to show EA squared is EB times EC. Well, kind of going in circles here. We want to show XM is parallel to AC. Which would mean that AXMP is an isosceles trapezoid. No, we don't know they're collinear, but really, if we could show XA is tangent to the circle, then by the same argument, YA would be tangent, and then XA and Y would be collinear. So really, we just need to show XA is tangent. But XA is tangent is the same. I forgot how I did this, but it's the same as saying AP is parallel to XM.
Yeah, from angle chasing.
From angle chasing. So that's the same as saying XAPM is an isosceles trapezoid. Which is the same as saying AYCM is cyclic. Yeah, maybe this is an easy problem. So because PMC is equal to angle A, XAB is XMB is XYM. Okay. All right, so I think this is an easy problem. All right, so I'll delete. Oh, you assumed X, A, and Y are collinear? But we could let.
I think we should delete Y.
We should delete Y. Yeah.
Yeah, first to that AX is
Is
tangent.
tangent. Yeah. We want this circle, but we don't really need this circle. And we don't really need point Q anymore, right?
Actually, we used to construct the circle.
Yeah, we used it to construct the circle. Let's see. Yeah, because we could draw AX. Yeah, we want to show its tangent. So yeah, I don't know if we've used yet that M is, oh, I think we used that M as the midpoint earlier. So can we show XAPM is an isosceles trapezoid? So angle PMC, yeah, we want to use that this is tangent. Angle XMC. So angle XMP, we want to show that's AXM, but XMP is 180 minus PMC minus XMB. I wonder if it's just angle chasing here, because I think it is. Give me just a second. So angle AXM is equal to angle AXM is ABM. Yeah, so I'll write this out. So angle AXM is angle ABM. And then at the same time, angle PMX, right? So angle, I'll just say XMP is 180 minus angle PMC, which is So 180 minus XMB is angle XTM. So that's angle XTM minus angle A. Sorry, I might be doing some of this wrong. PMC is angle BAC. I think that's right. So we want to show these two are equal. XTM is 180 minus, oh yeah. That sounds like a good idea. So, in fact, we could just say angle XMB is half of angle XDM here. So this would be 180 minus half of angle XDM. XDM, okay, so XDM is 2XMB. It's 2XAB. So, but we don't know XA's tangent yet. Ah, okay. So XMB, really we could have just written XAB here. So yeah, I guess I feel like we're kind of going in circles. Yeah, we want to show XM is parallel to AP. Do you see the solution? Or maybe there's a step we're still missing? Oh, okay. Yeah, it seems like it shouldn't be that hard to show XM as parallel to AP, but yeah, I just don't see how to do it. Yeah, I just keep going in circles, kind of. Let's see. So yeah, XMP, it's 180 minus XMB minus PMC. XMB is half of XDM. So maybe I could write that. What can we say about angle XDM? So angle, since angle DMB is 90, angle DXB should also be 90, right? I guess not. Why is that? So, oh, because B is not the midpoint of arc XM.
Let's assume that A is tangent and prove that the circle of XTM is tangent to BC.
Okay, that's an interesting way to do it. So yeah, we want to show that this circle is tangent to BC. All right. So yeah, and another way would be showing that. So then we could kind of remove point D from the problem, I guess, right? Yeah, then we could remove point D from the problem.
Can you let TM and AC meet at a point?
DM and AC, so right here.
No, TM and AC.
So right here.
T.
Oh,
TM.
T, I'm sorry. Let me move the diagram a little bit just so we can see the intersection point. I think that should be good. Whoops, sorry. So that point, right? QDP is twice BAC. I think that could be true. I'm not 100% sure though. I think so though, yeah. Because, yeah, QDP, it's 180 minus QMP. And then I think an angle chase could get you to that. Yeah, we can prove that, yes. Oh, really? Interesting. So D is the circumcenter of AQP. Ah, that's interesting. So we have concentric circles.
But we know that DQ equals to DP.
So basically, we can use an angle chase to show that angle QDP. Oh yeah, okay. I guess it's not. Yeah, but we know QD equals PD because MD is an angle bisector by the angle chase I said earlier. So yeah, we can prove that D is the center of that circle. Feel like we're pretty close. I like Serdar's idea of we could let EA be tangent and meet it at X, and then we want to show the circumcircle of XTM is tangent to BC. And what kind of an angle chase should we do to prove that? So we could try to show that angle XMB is 180 minus XTM. Wait just a second. Show XAMB is cyclic. Oh, sorry. That's by definition. We want to show it the other way. So yeah, we could do it. We could try it that way.
Can you hide the circle of XTM?
Yeah. Can I delete F? Mm-hmm. Hold on just a second. APQ. So you want me to make the circle appear again, right? Oh, whoops, all the lines just reappeared. I didn't want that. I'm going to delete the stuff. So XMB is XAB, which is a CB if we assume it's tangent. So we want to show that XDM is twice ACB, is that right? Yeah. Let X be on the circle passing through T and M. And MX is parallel to AC. So first we kind of define X so that MX is parallel to AC and X is on the circumcircle of ABM. Okay. Let Y equal XA. Yeah. I'll give it a couple more minutes before moving on to the next problem. Yeah, the angle chase keeps going in circles, yeah. I'll be right back. All right, thanks for waiting. A few more minutes and then I'm gonna move on to the next one. So basically, can we show, yeah, we could show dA equals dP, and we can show dx equals dm. What else would we need to show that AP is parallel to XM? So D is actually the circumcenter of APQ. We showed that. And we showed that, can we show that triangle DAX is congruent to triangle DPM? So we have some of that information. All right, I think I'm gonna move on to the next problem. We can come back to this one later. Let's see. So the next problem. Oh, this one I tried it for a while. This one looks like it shouldn't be hard, but it's actually kind of tricky. I haven't been able to figure it out. But maybe you guys will have an idea. So we have a triangle ABC, and then D is pretty much any point on BC, and E and F, E is on CA, and EF is parallel to BC. And DE meets the this feels very similar because we have like the circumcircle of ADC and the circumcircle of ADB. And we want to see where DE and BF meet those two circles. So DE meets this circle at X, and DF meets this circle at Y. And D1 is the reflection of D across the midpoint of BC. So this we'll call D1. And we want to show D1XY is cyclic. Doesn't it look easy? Maybe it is, but yeah, I had some trouble with it. One second. Let's check the chat. The centers of those two circles, yeah. So that and that. And yeah, we want to show that's cyclic. Is YFXE cyclic? I think it is. Oh no, it's not. I don't know why I thought that. But I think so here's the thing. Yeah, we want to show that this is cyclic. But if it was, and I let the perpendicular bisectors of dy and dx meet at a point. So yeah, like the circumcenter of dxy. So I'll just do it like this. So this point right here is the circumcenter of dxy. And we want to show it's also so HJ let me make it look a little bit better. I think that looks good. So J is the circumcenter of dxy. Add the perpendicular to yx. I could do that. So we want to show angle YDB is angle YXD1, but YDB is YAB. Can I let AX? Yeah, I can do that. AHI is similar to ABC. That's because AHB is similar to AIC. And that's because that's just an angle chase, yeah. Interesting. So AHI is similar to ABC. Okay, what's your solution? Or once you think you have it, yeah, let me know. Extend D1F to meet the circumcircle of AFX. Okay, so I'm gonna delete oh, I'm sorry, AFY. Okay. So yeah, I'm just gonna delete AX and AY for now. So I'll draw the circumcircle of AFY. And we see where D1F meets it. So that's a point L. Oops. Name it Y1. All right. Similar for x1. All right. Sorry. So angle AXE equals AXD is a CD, which is AEF. Okay, so EF is tangent to both circles from that angle chase. All right. And then, let's see. And so the A median is its radical axis. Okay. So, so AG's tangent to both those circles. Interesting. I like it. And once we know that, and okay. So AG's tangent to both circles.
How do you know that it's tangent? It is the radical axis, but
So basically, so yeah, EF is tangent to both the two circles. So if L is the midpoint, oh, but do we know the two circles themselves are tangent? Yeah, I guess if we knew the two circles were tangent at A, then we would have LF squared is LA squared is LE squared. Actually, I'm not sure now. So that well actually I think it is true because yeah, if L is the midpoint of EF, then since EF is tangent to both circles, L has the same power with respect to them. So it lies on the radical axis, and A, yeah, so.
But it doesn't mean that LI is tangent to these circles.
No,
It's
it is
just
not necessarily
radical axis.
tangent to both of the circles, because then it would imply that angle BAC has to be right angle, but it is not necessary.
Okay, yeah, so yeah, no, it's not, I was wrong. It's not tangent to both the circles. It's just lies on the radical axis. Yeah. So that was my bad. So yeah, let me, maybe I could change the diagram a little bit just so that, kind of like that. So now you know, so yeah, it's not tangent. And although now I don't like where point J is. Maybe something like that. Okay. So since D1, EF is a trapezoid, if we intersect DE with D1F, it's collinear with the midpoints. Nice. I like that. So we could draw that point. All right. That's basically by Cheva's theorem. Yeah. And then by power of a point, we would have D. So because X, well, but XYFE isn't necessarily cyclic. By power of a point, EFXY1 is cyclic. Okay. Interesting. Okay, so I'll start writing this up. I can delete H, I, and K, right? And J probably, right? So let DF meet the circumcircle of AFY at Y1. I'll just say define X1 similarly. Then I'm gonna write out the angle chase you said. That means that EF is tangent to AFY. Oh man, gotta do this, I think. See if that works. Then similarly, EF is tangent to AFX or AEX. Let L be the midpoint of EF. Then EL squared equals LF squared means that L lies on the radical axis of the two circles. So let M be the midpoint of BC. So, so let G be the midpoint of BC. So I'll just say if you extend DF I'm going to try to do this quickly here, but D1F, DE, and AL concur. So Also, yeah, it's not hard to see AL and G are linear. And then basically AL, so D1F, DE, and AL concur. By Cheva. And D1F to meet. We'll just say that. All right. I'll say concur at a point M. And then should be DF and D1E. And then once we know that, we use power of a point to show EFXY1 is cyclic. Because MX, so yeah, I still have to see kind of how that works. So, basically by the radical axis theorem. So, because yeah. I'll just say define H as shown because I'm lazy. So, I mean, basically by power of a point, then we have MF times MY1 equals MH times MA is equal to ME times MX. Come on. And that means that EFXY1 is cyclic. And then by Reims theorem, or Reims theorem, I'm not sure how to pronounce it. I'm not exactly sure.
I didn't understand that either. How did we conclude from Reims theorem?
Oh, so maybe you could just finish it with an angle chase, because angle M. Yeah, I'm not sure actually. I guess because okay, we want to show Y1X D1D. Huh. Yeah, so somehow they're the same circle, it looks like, but I think we have to prove that. Yeah. So I'll start out by using Rimes theorem. So, or Reims theorem. Y1, X1, D1, D is cyclic, but somehow it's the same circle. So let's see if we can prove that those are the same circles. Whoops, this should be a Y1. Anmol, do you see, I don't know, is it obvious that this circle also passes through X and Y? Maybe it's just an angle chase. Because we want to show, like we could try to show angle Y1, YX is 180 minus Y1. But that would still be tricky. Yeah. By a similar argument, YX1, D1D. Oh, because I put ones here. So okay, so this should just be X. And then this is just X. And then I'll say similarly X1, like similarly X1Y D1 is cyclic. And then, whoops. Yeah, it seems like we're pretty close. Angle Y, Y1D equals angle Y. Okay, so I'm going to write that out. So Y, Y1D is Y, Y1F. I'm confused about that. D1. Y, Y1. I think you mean Y, Y1D1 is Y, Y1F is YFE. Yes. Okay. YFB, and that's angle YDD1. And that means that DD1Y, Y1 is cyclic. Let me write this out and see if it makes sense. So then we have this. So, okay, so we're saying y1d1 is y1f, which is yfe. Yfe is yd1. So that's cyclic. So dd1y, y1 is cyclic. Similarly, dd1x, x1 is cyclic. Is that enough to solve it though? Because like, oh yeah, that solves it. All right, very nice. Thanks a lot, Anmol. That was a cool one. I will move on to the next one. Okay. This one is like with a right triangle. Well, let me check some of the other problems just to see. Yeah, this one looks. I'll try this one. This one looks kind of interesting. So we have a triangle with AX center IA. Sorry, I'm going to put BC as the bottom side. So we draw the X center. Couple angle bisectors. Oops, sorry. So I'll draw the X center. Using the Incenter X center lemma. Okay, so this will be the X center right here. Could also draw the X circle. And so X and so we draw the angle bisectors of B and C. Okay, so this is the incenter. We can call it I. And we drop perpendiculars. So from B to this angle bisector and C to this angle bisector, and we call it X and Y. And I'll just write this one for the heck of it, because then I is the orthocenter of that triangle. Don't know if that really does too much, but figured it's just worth drawing. So the circumcircles of IABX and IACY meet at a point P. It looks like P lies on the angle bisector. So not sure if that's obvious, but that's what it looks like. And we want to show that angle BJC is 90, where J is the incenter PXY. Interesting. So well, so maybe it's worth drawing this circle through BXYC. So basically we're saying that this point right here is the incenter. That seems weird. Because like the incenter of PXY you'd think would be like, I'm not sure if I did something wrong here. So we want to show BJC. You guys kind of see why I think I might have messed up. So is the incenter triangle center 1? I think it is, right? Oh. Wait, what's going on here? Is it making F and P the same point? I'm confused. Yeah, that doesn't make any sense. Wait. F equals triangle center P comma X comma Y comma 1. What? Oh, are they collinear PX and Y? Yeah. But then the problem
When you
statement.
hide the circles, I cannot understand anything.
What?
Can you hide the circle of BIC and X circle?
Yeah. I'll hide a bunch of stuff, but I wonder if like the problem is like correct. That's weird. So I probably don't need this point H. I'll hide it for now. Yeah, I think there might be something wrong with the problem. And we could try showing X, P, and Y are collinear, but this doesn't seem true as the problem is stated. So this point right here would be the point. Maybe J IABX. Let's see. So this is IACY and IABX. They meet at P.
Maybe we should draw IABY.
Or maybe what?
IABY.
ABY.
No, IABY.
Oh, IABY. Okay, so maybe it's IABY and IACX. Okay, so that's true by power of a point. Okay, so maybe the incenter of fxy, maybe they just wrote the problem wrong. Let's try it. So J center fxy1. Yes, okay, so that it looks like that should be the problem. So yeah, there was a typo in it, but it should be IABY and IACX. Interesting. So yeah, I could delete P. And there we go. Do you want me to unhide the X circle? Or just, yeah. So yeah, we want to show that J lies on this circle. So I could hide the circle.
Well, this is just angle chasing.
Really?
Yeah. It is easy to find the angle YJX.
Mm-hmm.
And we know that XCY equals to A over 2. And we are done.
Ah, yeah, that's too easy because then we know YJXC is cyclic, right? So YJX, we can find it in terms of
We can find that XCIA equals to 90 plus A over 2.
because let's see, so YJX.
Michael, if you call M is midpoint of BC,
Mm-hmm.
yeah, and you prove that Fy Mx is cyclic.
Okay.
That will show solve the problem.
Okay. So because GX is equal to GY, but once you show F lies on that, then it makes it kind of easy, is what you're saying.
Yeah, I think we just need to use angle J. Just can play angle BFC and angle XGI.
Okay. Do you guys want to move on to the next one, or do you want to type this up? It's up to you guys.
Let's go on. That was easy.
Okay. Second. Here's that problem. Okay. I'll try that. I'll do this one. So we have a right triangle. Oops, sorry. And then we draw the end circle. Whoops, sorry. I think someone's playing music outside my house, so you might hear it. So the end circle is tangent at A1, B1, and C1. There we go. B1 and C1. A1 and, okay, so we draw AA1 and we let it intersect the circle at D. So AC1I B1 is a square. Oh, it's already B. Then we reflect A1 over B1 and C1. And it's E and F, which is nice because it's already E and F. Oh, but I did it in the wrong order. So I need to make this E and that F. And so EF is parallel to BC1. And so those are homothetic. So let K be the foot of the perpendicular from E to A1F. Okay, so we kind of make a little orthocenter here. So K and L. Whoops, let me close this. Sorry. K, that's K. This is L. Prove that B1, C1, KL, and the perpendicular through D to AA1 are concurrent. Okay, so let me hide some stuff. We want to show that these three concur. So it looks like KA and L are collinear. Yeah, there's two J's. It's supposed to be the USA Junior Math Olympiad. So two J's. I feel like I've seen before that KA and L are collinear and parallel. I don't remember exactly the proof, but let's see if it's easy to think about. And then I wonder if it's just like Desargues or something. Because, yeah, we could label this point right here. So that the topmost point, let's see. KL is parallel to BC. Okay, so that's just an angle change. Yeah, because triangle KAC1, I think, yeah, we could show is similar to A1C1B.
We can delete EF then.
We can basically delete E and F. Yeah. Once we know that.
We don't even need these segments and K and L. Just need to prove that the intersection point of DG and B1, C1 is on the line from A parallel to BC.
Yeah. So, yeah, we don't even really need K and L, you're right. So can we show I'll call it something else, call it J. We want to show AJ is parallel to BC. Feels like, so J lies on the polar of A. So A therefore lies on the polar of J.
And delete K and L.
Yeah. Whoops, sorry. Actually, yeah, I'm gonna projective with the midpoint of BC does the job. Okay. Yeah, this looks familiar. So if we just call this M, so what are we projecting onto? So we want to show,
Can you draw AM?
yeah. So these three concur by the Iran lemma.
So we only need to prove that B1, C1 and J is a harmonic bundle.
Okay. B1, C1, and J, Jn are harmonic. Yeah. Which is the same as saying, yeah, N lies on the polar of J. Project through D, project A through D, or what do I guess we probably have to use somewhere that ABC is a right triangle, right?
Can you let AG hit the circumcircle, incircle again?
Yeah, so AG, so yeah, I'll label both these points.
So does it lie on A1G?
Does what lie on A1G?
J, O point.
Oh, J. Whoops, sorry. Project, I'm just reading C1, B1, and J. Interesting. Yeah, it does. So project C1, B1, N, and J through G. What do I project onto? The circle? So
Edge
then
onto the circle.
onto the circle.
So we
And-
don't need the angle BAC is 90
Is
degrees.
right. Yeah, we didn't even use that. Yeah. Oh wow, this is trivial. Sorry for the trivial problem. All right. Oh, we needed to show KL is parallel to BC. Oh, we need it for the very first step, where we showed KL passes through A. Interesting. That's kind of silly. All right, let's check out, let's see, one last problem. Oh yeah, we only have 3 minutes. Maybe I'll just go back to this one. Yeah. Yeah, I feel like we got so close here. It can't be that much more. Yeah, hopefully the YouTube viewers won't be too upset that I didn't type up solutions to 2 of the problems, but yeah. Okay. Okay. Yeah, so I'll try to include, the solutions when I send the GeoGebra files. But yeah, I really like that, solution that you had, Anmol, with the X1 and the Y1. That was an interesting solution. All right. All right, I think I'm going to stop right here and leave this last problem for the viewers to finish. So thanks everyone for participating again today. This is cool. We had a lot of good solutions. And so if you'd like to participate in future sessions, feel free to email me at mgreenb801@gmail.com. The sessions are on Sundays. So it used to be 9 a.m. Central Time. Now that there was daylight savings, it's 8 a.m. US Central Time, just because the US does daylight savings time. But if you're in a country that doesn't do that, you don't have to worry about it. It's at the same time as last week. So thanks everyone again for participating, and I'll see you all next time. Have a good one.